I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics: Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. I was happy that all of you guys finished the exam within the window. So what?
No Fs, right?
No Fs. I'll give you those at the end, but I was pleased. So there's a good distribution of grades, and so it's a good reflection of where people are at. I wanted to cover a couple things because I'm realizing as everything that we learned from exam one is sort of the foundation for the rest of the stuff that we're covering. So if there's a problem on the exam that you got incorrect, go check the solution so that you can orient yourself and make sure it's making sense to you. But a couple of things I just wanted to cover that were general themes is that quantitative variables provide more information than categorical variables. And I mean this more in like a precise way. Some of you guys had creative answers that because of the way you articulated yourself and the argument you gave, you actually got points if you could convince me that categorical variables could provide more information. And so that was good. But the main point of this question is that, so like with age, if you have age as a quantitative variable where you have 1 year, 2 year, 3 year, like how old you are, that provides more information than if you just know what age range the person falls into. And so if you said, are you in your 20s, 30s, or 40s, that's a categorical variable. And if you have categorical variable, all you can really find out is the proportion of people that are in that category. Whereas if you have it as a quantitative, you can find the mean age, you can find the standard deviation, you can do correlation with other things because you're looking at the whole spread of values. Whereas if you just have categories, you can't even find the mean age because if someone's in their 20s, that could be anywhere from 20 to 29. And if you have 1,000 people in there, it's just impossible. So quantitative variables are always, in a sense, better to work with because you have more information. And more so, you can always take a quantitative variable and turn it into a categorical. But you can't turn a categorical into a quantitative. So with age, you could start off with a quantitative and then say, hey, I want to put them into age groups. So then you can convert it to a categorical. Here's another one that came up that I think will be important. Regardless of the distribution of the observed sample statistic, no matter what the shape of it is, the distribution of the sampling distribution will always be symmetric and bell-shaped. And mainly because it contains the values of the sample statistics. So let's say we did have age and it was really skewed in some way. The sampling distribution is taking the mean value. And so the mean value is going to be a point, and then you put it in your sampling distribution, and then you do 1,000 samples. And so the means are all going to kind of be right around each other, and they're going to form a bell-shaped symmetric curve. And this will come up even today as we're looking at distributions. Okay, here's another one that came up, the third part of the Gallup study question. You had a poll of the proportion of people who approved of Obama's job as president in June, and that was 0.49 with a margin of error of plus or minus 3 percentage points. And then the poll was taken a month later, and the point estimate was 0.44 with a margin of error that you guys calculated. And so then the question was, in June it's 0.49, the approval rating, and then in July it's 0.44. Can we say with 95% confidence that his approval rating actually decreased? Is there a significant difference between 0.49 and 0.44? This was a tricky question because it kind of draws from things in two directions, like confidence intervals and then significance tests. But the way, if you look at it, here's June and then here's July. So the point estimate was 0.49, and then you guys calculated the 95% confidence interval, which was here, 0.46 and 0.52. So this confidence interval is saying that we're 95% confident that the true proportion of people who approve of Obama's job as president is between 0.46 and 0.52. So we're 95% confident that it's somewhere within here. And then with the July, we also calculated the 95% confidence interval. So the point estimate was 0.44, and then the 95% confidence interval is between 0.414 and 0.466. And so it's saying that we're 95% confident that the true proportion of people in the US who approve of his rating is within this range. And so the reason why the difference in proportions is not statistically significant is because the true population value in June and in July could have been right here, 0.461. The confidence interval sort of provides the plausible values for the population parameter. And so, in a sense, a plausible value within sort of the 95% confidence interval could be 0.461, both in June and in July. So then another thing, and this has come up a handful of times, that the observed sample statistic for the hypothesis test is the statistic for which we want to know how likely it would occur by random chance if the null hypothesis was true. And so the key phrase here is the observed sample statistic. Another term for it is the test statistic. It's the value that you're going to be testing. We have our sample, and we want to know difference in proportions, and if the difference is significant. So the observed sample statistic is the proportion of men minus the proportion of women, in whatever that value is. That's the observed sample statistic. And it's also called the test statistic. But we'll be using that throughout the rest of this course. What is the statistic that you're going to be testing to see if it's significant or not? And then I think the last thing on the exam, the bank clerk promotion study, it was the very last question where it said, what if you did a random sample of all people who were up for promotion in 2011, and would that be evidence that racial discrimination is happening? A handful of you said that no, it wouldn't, because it's just one random sample and that can't provide sufficient evidence. Actually, one random sample can provide sufficient evidence. I mean, that's what we do in this course and in social science, is that we often only have one random sample, and then we do the hypothesis test, and you can determine whether or not it's significant. But the actual right answer to this question, it was no, but it was because it's an observational study, and you can't make causal claims. Like, you can't say that white bank supervisors are discriminating against black bank clerks based on just an observational study, because there's other confounding variables, such as the white bank clerks might have better resumes than the black bank clerks. And it was in the experiment that we could control for all those confounding variables and randomly assign who got the resume. So the main point of bringing up this is that with one random sample, you can get sufficient evidence. You don't need multiple samples to get it. So we're in a transition phase in this course, and we're going to be taking everything that we've done up until this point, looking at it from a different vantage point. And so there'll be a lot of familiar things, but we're going to stepping it up one more level to see, okay, how do we put this into practice for everyday research? And so you'll see familiar things, but we're going to be looking at it from a slightly different perspective. Today's focus is on normal distributions and what those are all about and how central they are to statistics. First is what density curves are. So the density curve reflects the overall pattern of a distribution. And a distribution is just all the values that you're looking at and how they're spread out along the x-axis. You have your histogram, which is all your values stacked up, and so it shows you the distribution of values. And then the density curve is a curve that's imposed on top of the histogram, just to show you more mathematically what is the actual shape and spread visually with a curve. And then there's some characteristics of this curve. And one important one is that the total area under the curve is 1. It encompasses 100% of the distribution. One of the reasons why it's called a density curve is it shows you where the concentration of values are. As you go up in the scale, you have a higher concentration of values, and then as you go down, there's a lower concentration of values. So it's how densely packed the values are in the distribution. The area over any interval is the proportion of the distribution in that interval. Like the range for 95%, if you cut it here and cut it here. So the area over that, 95% of the values are contained within that. And so, again, if you did the whole curve, you would have 100% of the values. Again, this is stuff that we've already covered, but this gives it more of a formal definition. So we've been talking about bootstrap and randomization sampling distributions, and so these distributions have some unique characteristics of all types of bootstrap and randomization sampling distributions. Here's different ones that have come up either in the lectures or in the course. For each of these, what does each dot represent? Whether it's a bootstrap sampling distribution or a randomization sampling distribution. Chelsea? People. So the sampling distribution.
It's sample.
Yes. This data set is looking at restaurant tips. It has a sample of the amount of tip that people gave at the restaurant, and they calculated the sample mean, the mean tip value, and then using bootstrap sampling, they generated 1,000 replications of that initial sample and got 1,000 sample means. That's why you see that they all sort of follow a similar density curve, which is this bell-shaped symmetrical distribution. And what these ultimately are what's called a normal distribution. And so an important thing that we'll be moving forward with is what is a normal distribution. And it's the symmetric bell-shaped curve that we've seen in most of our bootstrap and randomization sampling distributions. It's called a normal distribution, and it follows a normal density curve. And so normal has a unique meaning in statistics, not like in the social world where normal means something and abnormal means something, but it has a distinct characteristic. It's symmetric, it's bell-shaped, and you can tell very quickly the mean and the median are going to be the same value, or more or less the same value, right in the center. We're going to be working with normal distributions a lot, and one of the theorems that is extremely beneficial when working with normal distributions is that for a sufficiently large sample size, the distribution of sample statistics for a mean or proportion is normally distributed and is centered at the value of the population parameter. We have our one sample, and let's say we want to do sample mean, and then say we did do 1,000 samples. The distribution of our sample means is going to be normally distributed, which is the bell-shaped, symmetric. And if we were taking 1,000 samples from the population, our distribution is going to be centered at the population parameter. A way to look at this is there's little things online that help us. In the top here is a population that we're pulling from, and let's say it's something like age. And so we actually know the population mean is 16, the median is 16, standard deviation is 5. And if we say we're going to do a sample of 25 from this population and calculate the sample mean, so if we do one sample and we pull down 25 people randomly, and then we have our one sample mean. So this is our sample of 25. And if the sample size is large enough, the distribution of this will look like the distribution of this. And then if we take 1,000 samples, we can get 1,000 sample means. And the distribution of our sample means is going to be normal. So then we do 10,000, and so what it shows you is you have a normal distribution. So what if we then change this up here to a skewed? So here's like an example of a skewed one. This is another population. This might be something that's a count, like I was going to say number of kids, but the mean value is 8, so that's probably not a good thing. But we'll say it's like income, where there's some people who are super, super wealthy. But our population, for the characteristic that we're looking at, is income, and it's very skewed. What does it look like if we just do one sample? What do you guys predict that the distribution of our sample will look like? What do you say, Brittany?
It'll be skewed as well.
Okay. And then what will the distribution of our sample means look like?
This one's skewed.
Yeah, how many think this one will be skewed? Well, let's look at it. So we do our one sample of 25. If we did like 100, the pattern would show even more, and that's why we typically do samples of more than 25. But you're right, it's skewed, but then let's see what the sampling distribution looks like. So we do 10,000, and it actually ends up being normally distributed. And I'll do it slowly. So here's our one sample, and then it drops it down, and then we'll do it again. So what it's taking is all of these values and calculating the mean, and it's going to be close to the mean of the population. The reason why this is going to begin to be normally distributed is taking the mean value of all of these. And so it's always going to be hugging around close to each other. The fact that it's skewed won't matter because that's taken into account when you take the mean value. And so if you keep doing it, you're always getting the mean value of your sample. This will be an important thing to conceptualize, or to at least convince yourself of, that even if values in the population are skewed, when you're just looking at the mean or the proportion, the distribution of that value will be normally distributed. It says that the central limit theorem holds for any distribution of values. And then the criteria for being sufficiently large sample size will vary. But even with 25, you saw that that skewed population parameter ended up being normally distributed even with a sample size of 25. So the criteria for sample size isn't like this huge number. It's actually a fairly small number, but there is a threshold. And the more skewed the distribution of population values is, i.e. the farther it is from being normal, the larger the sample size has to be for the CLT to work. If you know that the thing that you're measuring is highly skewed, you want to amp up your sample size. For distributions of a quantitative variable that are not very skewed and without large outliers, having a sample size of at least 30 is usually sufficient to use the central limit theorem. For distributions of a categorical variable, where you're looking at proportions, counts of at least 10 within each category is usually sufficient to use the central limit theorem. Right now, the categorical variables that we've looked at are binary. It's either like male or female. But like if we look at a variable like race, where you have white, black, Hispanic, Asian, it's just saying that you need to have at least 10 people who are fitting into each of those categories in order for what we're doing to move forward. And everything that we're going to be looking at will meet this criteria, but you might be, as you do your final research project, something that you're really interested in, and you're doing race and you want to know things about Native Americans, but your sample only has 5 Native Americans. That's less than 10 within the category of Native Americans, and so you really wouldn't be able to do this type of statistical test on that. Something to be aware of. So normal distributions are characterized by their mean and standard deviation, and they're always notated in this way, where capital N in this context means it's a normal distribution. And then anyone know what mu refers to?
Population.
Nice. Population mean. So the mean, and then what's sigma? Standard deviation. So learn this notation, and even like this type of thing, that might be all the information you get. And so you would have to know that this is representing a normal distribution with a mean of mu and a standard deviation of whatever's in the sigma. So what would be the center of this distribution?
Mu.
Yes, whatever mu is. Because we know it's normally distributed, that it's bell-shaped and symmetric, there's a lot of things that then we can pull from this just by having very, very little information. But as you can see, it's drawing on stuff that we've already addressed and have already calculated in different ways. So n indicates that the distribution is normal, mu represents the mean of the distribution, and sigma represents the standard deviation. As Brittany was saying, the center of the distribution is mu, and then if you go out 2 standard deviations, which is mu plus 2 sigma. You hit the upper bound of the 95% confidence interval, and then minus 2 sigma is the lower bound. This is stuff that we've seen, but it's putting it into a more formal definition. If we look at this as the normal distribution, okay. So this is like our bootstrap sampling distribution that we've done, where it has this characteristic. If we were going to define what this distribution is, so I wouldn't even have to show you the picture anymore. I could just say we have a distribution that's n with 0.523 mean and 0.048 standard deviation. You can see the mean of the sampling distribution is 0.523, and then the standard deviation is 0.048. Instead of having to draw pictures and stuff, you can just say, this is our distribution. It's normal, here's the mean, and here's the standard deviation. And it doesn't have to be precisely normal. It's more about if it's close to being normally distributed, it has these characteristics. So if a bootstrap sampling distribution is approximately normally distributed, and what is the bootstrap sampling distribution centered on? Is it centered on the population parameter or the sample statistic?
The sample statistic.
Okay. You're exactly right, that bootstrap distributions are centered on the observed sample statistic because you're generating it from your observed sample, and it represents the variation in the sample statistic. And then the standard error, you want to know what the standard deviation of the sampling distribution is. This is trying to reinforce what the notation is and how it can take this vast amount of information and put it down into a simple symbol that you can then easily work with. So if a bootstrap sampling distribution is normal, you can find p confidence interval by finding the middle p% of the distribution. Sometimes having p% makes it confusing, but you can find the 95% confidence interval by finding the middle 95% of the distribution. So if this is our notation, we have the sample statistic and then the standard error. We'll do an example. This is a poll on the Oscars, the most recent Oscars. It says, according to this poll, 15% of the people thought that the artist should win the best picture. So we have right here the artist in the poll, 15% thought it should be best picture. So p hat is 0.15, so that's the proportion of people who voted for the artist. How would we calculate the standard error for this sample statistic? So based on, from your guys' what we did the previous weeks, how would you go about finding the standard error for this sample statistic? So we're wanting to know how this sample statistic varies across multiple samples. If we resampled from the population, what would the variation in that proportion be? And we're ultimately wanting to calculate the confidence interval for this point estimate. Do we do randomization sampling distribution or bootstrap sampling distribution when we want to do confidence interval? Bootstrap is typically when we do confidence interval, and randomization is when we're doing hypothesis tests. We'll go into Lockstat, and we're going to do bootstrap confidence interval. Which one would we be selecting? So we do confidence interval for a single proportion. So then you go in here and you say edit data, and it says count. Count is the number of people that are in that category. And so that was 22. And then n is the sample size, 141. And then we'll run our 1,000 samples. And so if we want to find the standard error for the sample statistic of p hat, it's right here. And the standard error is the missing piece when we're doing a lot of stuff. You have your point estimate, you have your sample size and all that, but the thing that we just never know is the standard error. And this is going to be a major focus of moving forward, is what are the different ways to calculate the standard error? Because once we have the standard error, then we can calculate the confidence interval, we can do hypothesis tests, because then we'll have all the information we need. But the most difficult piece of information to gather is the standard error, because you can't just look at your sample and say, okay, what's the standard error of this statistic? You need to do bootstrapping. So in this case, we have standard error of 0.03. Why this is important and sort of how this relates to density curves is the area under the curve of a normal distribution is equal to the proportion of the distribution falling within that range. And so when we're talking about proportion of values falling within a certain range, what does that remind you of? Yep, or p-value.
P-value.
Just, but you're right, you're in the right range. So again, you're seeing stuff that we did before. P-value is looking at the proportion of values under that part of the curve, and that can be spread out to looking at the whole curve. And it says knowing just the mean and the standard deviation of a normal distribution allows you to calculate areas in the tails and the percentiles. It's stuff that we've been doing through a more complex and convoluted way of finally getting to what the p-value is. If we know the mean and the standard deviation of our distribution, then we can much more quickly calculate, here's what the p-value is, here's what the 95% confidence interval is. And the reason why we can do all this is if our distribution is normally distributed, if it has these characteristics of being bell-shaped and centered where it's symmetric, we can look at some examples. Here's a normal distribution, and let's say 0.156 was the mean value and the standard deviation was 0.03. So 0.156. If we want to know the 95% confidence interval between -2, this is an example where we have a mean of 0 where it's at the center and a standard deviation of 1. And if we go out 2 standard deviations this way and 2 standard deviations this way, it calculates for us that the area under the shaded portion is 95%. So it's a quick way of showing you here's what the 95% confidence interval is. And you can plug in whatever values you're working with of your normal distribution. You put in the mean here and the standard deviation here. So then if we want to just look at the distribution that's above 2, what do you think, if we're just looking at this shaded area above 2, what proportion of the normal curve will be above 2? 2.5%. Let's check. 0.023. So you can also go down here and you can control what you put in. So if we say the shaded area is 0.95, what's the range for a 95% confidence interval? And so we say what's in between. This does it the reverse way. And we've been saying that 95% confidence interval is -2 to 2. Technically, it's -1.96 to 1.96, but it's fine to round off to 2. But basically, what this little applet does, or what you could do with a chart, is if you have the mean and standard deviation and you want to know what's the 95% confidence interval, there's just a standard quick calculation that you can do that you don't even have to count out the numbers. It can be done automatically. We'll come back to this, but you're going to be using this for like the homework assignment, and anytime that it asks you where you want to know the 95% confidence interval, you can just come right to here and plug in mean, standard deviation, and if you know the confidence interval, you plug that in, or if you know what your cutoff points are, you can plug those in. In some reason, I couldn't get this part to work, but basically you plug in 0.156, which was the mean for our Oscar study of whole, and the standard deviation was 0.03, and then the shaded area, which is the 95% confidence interval, it just provides it for you right here of what that range is. It's the same as going out 2 standard deviations to the right and to the left gives you the 95% confidence interval. So we've actually calculated this before, but now if we can definitively say, yes, the distribution is normally distributed, then it has characteristics that allows us to then work with it more efficiently. Confidence interval is p hat plus or minus 2 times the standard error. And so we did it with the bootstrap sampling where you find the lower bound and the upper bound. There's multiple ways to arrive at the confidence interval, and so this is going to show you, okay, yes, this is the 95% confidence interval, which we've already calculated, but then we're going to expand beyond the 95% confidence interval. For a normal bootstrap sampling distribution, the formula sample statistic plus or minus 2 times the standard error gives the 95% confidence interval. So this is something that we're familiar with. How would you use the normal distribution where it's centered at 0 and has a standard deviation of 1 to find the appropriate multiplier for other levels of confidence? Why do we use the number 2 right there?
It takes 2 standard deviations come up with z-score, which sets up confidence.
Exactly. The 95% confidence interval is 2 standard deviations from the mean. But like the 99% confidence interval how many standard deviations is the 99%? Yeah, it's 2 point something, like it's not a clear cutoff. We could do it before kind of quick and easy with the 95% confidence interval because we just knew that the 95% confidence interval is 2 standard deviations away. But what do we do if it's something other than the 95% confidence interval? This is where having it be normally distributed, there'll be an efficient way to calculate that out. For an X% confidence interval, use the formula, our sample statistic plus or minus Z star times the standard error. And Z star is the Z score that corresponds with the desired level of confidence such that X% of a normal distribution is between negative Z star and Z star. In the way that we've been doing it, Z star corresponds with the Z score of the confidence interval that you're interested in. What's Z star for a 95% confidence interval?
2.
Yes. So then every point on the normal distribution has a Z score or a Z star. And so you have to say, well, what point am I interested in? And then calculate the confidence interval by using that point that corresponds with the appropriate Z score. So every point has a Z score. Just like when we looked at someone's height, you could find out what's the Z score of a person's height. So in the same way, we're using Z score to then get the confidence intervals. As we've seen before, confidence interval for 95% is roughly -2 to 2. So that's negative Z and positive Z. Find Z star for a 99% confidence interval. And there's tables in your textbook that you can use where you just look up 99% and do it, or you can use things like this where you want to know the confidence interval for a 99%. So the shaded area, the area under the curve is 99, so you click between. What that shows you is for a 99% confidence interval, it's negative 2.5758 to 2.5758. So you can say whatever confidence interval you want, let's say a 90% confidence interval, and it gives you the Z scores or the Z star that you need. If your mean and standard deviation are different from 0 and 1, you just plug in the appropriate mean and standard deviation. But the key thing here is you'll be asked what is the Z star for the particular confidence interval that we're wanting to calculate. So a national survey shows that the majority, this is an example, majority, 64% of American adults use at least 3 different types of media every week to get news and information about their community. The standard error for this statistic is 1% or 0.01. It says find the 99% confidence interval for the true proportion. So we know the sample proportion is 0.64 and we know the critical value of the standard error is 1% or 0.01. And so those are the 2 pieces of information that we need to do a lot of different analyses. And so one is find the 99% confidence interval of the true proportions. 0.64 is our point estimate, and we want to know what's the 99% confidence interval for that point estimate. Confidence interval is the sample statistic plus or minus Z star times the standard error. And Z star corresponds with what? The Z score for a 99% confidence interval, the upper bound is 2.5758. And so that's the value that we'd use in calculating the confidence interval. This is our sample statistic. This is our Z score associated with the 99% confidence interval. And this is our standard error. So that was confidence intervals. And then the other main thing that we do in this course is hypothesis testing. And so these concepts carry over into hypothesis testing. So a question is, are firstborn children actually smarter than subsequent born children? That's the research question that they're looking at. So based on data from the student survey, we'll test whether firstborn children scored significantly higher on the SAT. The null hypothesis is that there's no difference. So no difference between the mean value of firstborn SAT scores versus the mean value of not firstborn SAT scores. So the difference would be 0. The alternative hypothesis is that the mean value of firstborn SAT scores is going to be greater than the mean value of non-firstborn SAT scores. The important thing when you're doing hypothesis testing is what is your observed sample statistic? The observed sample statistic that we're interested in, that we're going to be testing, comes from the alternative hypothesis. So we have here the mean value SAT score for firstborn minus the mean value of non-firstborns is 30.26. So it's basically saying that firstborns had an average SAT score that was 30.26 higher than the non-firstborns. This is a difference in means hypothesis test that we're doing. So this is our point estimate of the difference in means of firstborns to non-firstborns in SAT scores. And so we kind of want to know, is this difference in means statistically different from zero? Does the confidence interval of this point estimate, does it overlap with zero or not? Because if it overlaps with zero, then it's saying it could have occurred by chance to be that large. And then what we've done before is based on a randomization sampling distribution, our standard error is 37. The two key values that we need when we're doing confidence intervals in a hypothesis test is the sample mean and the standard error of the sampling distribution. You gotta like scan all over the place to say what's the mean or what's the sample statistic and then what's the standard error. What normal distribution should we use to find the p-value? You need to know which notation to use in order to then move forward with the test. So if our sample mean is 30.26 and standard error is 37, and we're going to do a hypothesis test on this sample statistic, what normal distribution are we going to be looking at? We basically are testing under conditions where the null hypothesis is true. And so when the null hypothesis is true, the difference in sample means equals zero. But the standard error is still going to be the same. So that's why we'd use this normal distribution. And where this value comes in, that's our observed sample statistic, and we want to know where it fits on the normal distribution. So if it fits way out here, we know the proportion of values that are as extreme as that is going to be really small, and so then we could reject the null hypothesis. This brings in the p-value. It says the proportion of values as extreme as the sample statistic occurring by random chance if the null hypothesis was true. Because this is a hypothesis test, we want to see what would happen if the null hypothesis were true, i.e. the difference in mean scores equals zero. Thus, the sampling distribution should be centered around zero, and the variability of the statistic is equal to the standard error. So it's restating what we've already looked at, but looking at it in the context of a normal distribution. So with hypothesis testing, this is our sampling distribution as if the null was true. And so here's our observed sample statistic right here on this distribution, because you want to know where it's located on the distribution. So whatever the value of your observed sample statistic is, that's its position on the sampling distribution. And then the p-value is the area under the curve that's extreme as the observed sample statistic. P-value is the proportion of values as extreme as observed sample statistic occurring by random chance if the null hypothesis was true. The sampling distribution when the null hypothesis is true. And then what you want to find is where does the observed statistic fit on that distribution? What's its location? And then you calculate the p-value as being the proportion that's as extreme as the observed sample statistic. Another way to look at p-value is the probability of getting a sample statistic as extreme as the observed sample statistic by random chance. If the randomization sampling distribution is normal, which it is in all of our cases, the p-value is the area of the tails beyond the observed sample statistic of the distribution, where the null value is the mean and the standard error is what we have from the sampling distribution. It's taking the stuff that we've learned and showing how it can be simply represented with this notation. Once we know that it's normally distributed and we know our mean and our standard error, we can just go look up on a table or a computer what the confidence intervals or p-values would be. Back to the firstborn children, the distribution that we're going to be looking at is where the null hypothesis is operating, so it's going to be a mean of 0, and then 37 is the standard error, which we calculated. And then our observed sample statistic is 30.26, which is the difference in mean scores between firstborns and non-firstborns. And so then we can go back to here. Mean is 0, our standard deviation is 37, and our sample statistic is 30.26. So we're wanting to know what proportion of values are greater than 30.26. That's why we use the above. What this shows us is that the proportion of values that are as extreme as our observed sample statistic is about 20%, 0.206. Does anyone know what this value is, the shaded area, the proportion of values that are as extreme as our observed sample statistic? The p-value. I mean, this is just a replication of our sampling distribution. It has a mean of 0, a standard deviation of 37, and we want to know the proportion of values that are as extreme as our observed sample statistic. And so our sample statistic is 30.26. You want to know where does it fall on this distribution, and it's right here. Because it's normally distributed, we can just plug in the values, and it will generate what the p-value is. Before, it used to be tables in the back of the book, and you'd have to, well, I don't even know how they would do it, because there's always different means and standard deviations. So this is a very simple way to calculate the p-value. And this is how you would be doing it for homework assignments and such. So the probability of getting a sample statistic as extreme as the observed sample statistic just by random chance if the null hypothesis was true is right here, 0.207. So we looked at normal distribution. The more general is called the standard normal distribution. And so in practice, it's easier to use one normal distribution when doing inference, and so a standard normal distribution to make it standardized. And so the standard normal distribution is the normal distribution with a mean of 0 and a standard deviation of 1. So it's notated this way. What we're doing is, how do we take all these different normal distributions and find one standardized normal distribution, sort of like SAT, that is a standardized achievement test, so that you can have one standardized distribution. So this is what it looks like. It has the same characteristics except that it's centered at 0, and the standard deviation is 1, so you go out 2, and it's, again, going to be 95%. What we'll always want to do is convert our specific normal distribution, which is mu sigma, to a standardized normal distribution. And the way you do that, this will recall things that we've already done. You have a distribution of values, and you subtract the mean value from each of the values in your distribution to shift the center to 0. And then you divide the result by the standard deviation to stretch the difference to match a standard deviation of 1. So if x is a value on this normal distribution scale, then z equals your value x minus the mean of the distribution divided by the standard deviation of the distribution. And so if you have a sampling distribution that's normally distributed with a mean of mu and a standard deviation of sigma, if you take every value on that sampling distribution and subtract it by the mean and divide it by the standard deviation, you're going to come up with a new distribution that's in the form of a standard normal. What's interesting about that is that z, when it's on the standard normal distribution, corresponds exactly with the z-score. So x is a value on your sampling distribution. And when we convert it to a standard normal distribution, the x value gets converted into z, and that actually corresponds exactly with the z-score. Before, we used to say, okay, well, what's the z-score for a particular value? You'd have to do x minus the x bar divided by the standard deviation. Well, when we use a standard normal scale, whatever the point value is, that is the z-score. So it just makes it very simple for doing calculations. The standard normal curve is a distribution of z-scores. So it's like the value on the distribution is the z-score for that value. So I'm going to pass out the exam. The mean score was 72 to sort of set expectations. The max was 89. The min was 60. The standard deviation was 12. So you guys will be able to see where you fit. So all I did was the raw score. So you'll get 70 out of 100 or whatever. There's no grade attached to it. But if you're wanting to know what the grade might be, basically if you're more than 2 standard deviations above the mean, that means you're like, well, no one was more than 2 standard, but that would be an A plus. If you're between 1 and 2 standard deviations above the mean, that would be an A. Within 1 standard deviation above the mean would be A minus to B, and so on. One last thing. This is the correlation between the exam score and your homework assignments. So I want to see like if there's a correlation between how well you've done on your assignments and how well you've done on your exam, and we see a positive and fairly substantial correlation between your homework assignments and your exam grade. So sorry to throw in statistics into